chapter 14, section 14.1, 14.2 on integrals in R2. So essentially we start studying multiple integrals. All right, so let's again always keep in mind what we do for one dimension. So for one dimension, recall that the integral of a function, so the input space here is just R, right? And I have the output F, and the integral is a limit of sum. Okay, so the integral between x equal to a, x equal to b of f of x dx is the limit where essentially you sum all those rectangles under the curve is positive, and you multiply by the width, and this limit is when the width goes to 0, and this gives you the integral when it exists. Now, so we know that very well, and this integral is used for many things. Okay, so as we see from the picture, it means it equals the area under the curve, so you can use the integral to compute the area under the curve, but you can use it for many other things. So for example, you can also compute the average of a function. So what's the average? Well, you integrate from a to b. It's like summing all the values of the function in a way, and you divide by the length of the interval. That gives you the average of the function on the interval ab. Another use of the interpretation of the integral is in probability. If you have a random variable x that is continuous and has a PDF, so a probability density function little f, then if I integrate this PDF from a to b, this is the probability that the random variable takes value in the interval ab. Okay, and we also saw in this class that when I integrate, if I have a curve, okay, given by the parametric equation, so this is a curve in 3D, but it could be in 4D, 2D. So I have parametric equation, so the position at any time t is xt, yt, zt. Then the length of that curve from t is equal to a to t equals to b is the integral of the length of the velocity vector, okay, which is in that case is x prime square plus y prime square plus z prime square, square root of this whole thing, and then the parameter is t, I should put it, so the integral is over t, so it's just one integral. I have a square root. Okay, so that's for 1D. Okay, and we'll take a very similar, the integral in R2, R3, Rn. You have a very similar interpretation. Okay, so let's see what we have. Okay, now good thing to keep in mind is this integral in one dimension, the integral of f on the interval ab, has three important components. First, the domain of integration, which is the interval ab. Second, what you integrate, which is the function f. And third, and very important, tend to forget about this, we have this element of length, dx, which represent the element of this very small length dx, okay, which is the variable of integration. All right, so now let's write down an integral in R2. You also have these three parts. You have a double, so we use double integral because we have now in the input, in the domain is two-dimensional, it's R2. And what we have is also those three things. That is, we have the domain of integration, so that's a subset of the input space, which is just a subset of R2. We have an integrand, which is a function now of two input. And now we have also the variables of integration x and y, and the dx dy now doesn't represent together a length, but they represent an area. Okay, so this is the infinitesimal area. The infinite, if you think about it, it's like a very small square or small rectangle represented by dx dy. Okay? And so the double integral of f over the region A is, again, like in 1D, a limit of sum. And what you're doing is summing over, if you want, all the small rectangles, a small square inside A, and you take the value of f in every square, you multiply it by the area of the square, and you sum that over, okay? And the limit is when those square becomes very small. That's the double integral of f over the region A. Okay, now we're going to use this integral. So before seeing how to evaluate this, we're going to just talk about the interpretation of the integral and why is it useful. Well, one thing that is useful is that actually if I integrate just one, okay, so I integrate the function 1 over the region A dx dy. What you're doing here is really just summing the squares because the function is 1. And so the squares inside A. So what you get is when I integrate A dx dy, you get the area of A. And that's a non-trivial quantity because, for example, look at this A. This A is curvy, so the area is not so clear, right? So we didn't really have that in R because in R, well, the integral of a subset of R would give me the length of that subset. That's interesting, but that's a bit straightforward. All right, so that's the area of A. Second, well, like the area under the curve, now F represents a surface. So I can, if I integrate F over the region A, that gives me the volume under the surface F, okay, restricted in the region A. Again, the same way also, if I actually integrate over A the function F, but I divide by the area of A, this is the area of A, then that gives me the average of F, okay, in the region A. And along the same lines, in probability, if I have two random variables x and y, and they have a joint probability density function, PDF, f of xy, then the integral will give me the probability. So if I integrate the PDF over the region A, that gives me the probability that these two variables takes values in the region A. Again, that's two-dimensional. I have two numbers. Okay. All right. So we're gonna see these in different kind of interpretation as we go. All right. So the chapter 14 is not that hard, but we can make several mistakes if you're not systematic. Okay. And so here's how to avoid mistakes when you evaluate integrals. First of all, and that's the most important step, is to make a picture of the region of integration. I'll do an example, okay? So that's a step we don't really have in 1D because, well, we're on R and the region of integration is usually pretty straightforward. Second, I have integrals in X and in Y. I have two integrals. So I have to decide which integral I integrate first, okay? The order of integration. And once I decide what the order of integration I take, I find the bounds for each of my integral, okay? And it turns out that the order of integration doesn't matter in terms of the answer. You'll get the same answer. If your function is smooth, that's called the Fubini's theorem. And so you can decide whichever way you want to integrate. Sometimes there's a direction that is easier than others. We'll see examples. Okay, so, and number 3 is just integrate. You integrate exactly like R, one integral at a time. Okay, so it's like doing two one-dimensional integrals. All right, let's do it. So I'll just do one example. We'll do more examples in class. Okay, so here's the question. So we want to evaluate the integral of that function of two variables on the region, which is defined by x is smaller than bigger than one, is between 1 and 2, and y is between 1 and x. And already we see that there's something different. One of the bounds depend on x. One of the bounds depend on the other variable. Okay, so let's make a picture of that region. That's step 1. So x is between 1 and 2. Okay, so that's just the input space, right? It's not the picture of the function, graph of the function. We're just in the input space and we draw the region of integration. So x between 1 and 2, but y is between 1 and x. Okay, so 1 is clear, and x, I look at the function y is equal to x, which is just a straight line. So the region of integration is all the point whose x coordinates between 1 and 2, and the y coordinates between 1 and x. Okay, so this is that triangle. Okay, now I can decide to integrate x first or y first. So integrate y first would be to look at the integral. So go from, for fixed x, I integrate y. So the bounds would go from the bottom here to the top. And then I integrate x on the whole interval. So let's do that first. So I decide that I want to integrate y first, so fixed x. So I should say x is fixed. A bit like the derivative, we fix one, we integrate the other. Now y goes from 1 to x in that triangle. And then x, after that, goes from 1 to 2. Okay? So those will be my bounds. The bounds in y will be between 1 and x, and the bounds in x will be between 1 and 2. So if I write the integral, it writes like this. So the integral in y, and integrate from 1 to x, and then outside after that, I integrate x from 1 to 2. Okay? And now you just do one at a time. So we'll start with the inside one, the integral in y, for fixed x. So now x is fixed like a constant. And so I can integrate that. So if you just believe me, the answer to this integral, so again, 2x squared is like a constant, so I integrate y minus 2, I get this. I integrate 2y, I get this. And then my bound now is between 1 and x. So it takes another step just to put these bounds in. Okay? So I put these bounds in, I replace x here, get that, x here, I get that, and then I replace 1, I get this. Okay? Exactly like an integral in 1D. Now I have another integral, the integral in x. And then again, it boils down to a one-dimensional integral. I integrate this thing, I get this between the bounds 1 and 2. And if you do the calculation, you get 3. Okay? So step 3 is like doing two integrals in R, right? Okay. So that was for integrating y first with x fixed. Now let's do the opposite. What if I want to integrate in x first? Well, so I do again, I draw my region. It's the same region. The only difference now is I decide to actually, instead of actually fixing x and integrating y, now I fix y. So I first fix y, okay? So let's say what for y given y. So for a given y, x will go between this line to 2, and this line is y equals to x. So this region is all the x's for which between y and 2, and then y goes between 1 and up to here. I should put this is the point 2, 2, and this is the point 1, 1. So it's good to actually have a couple of points here. Point 1, 2. Okay. So again, x goes from y to 2, and then y after that, if I look at all my heights, it goes from 1 to 2. Okay. All right. So that's now my bounds. And the difference is now I integrated x first. And the bounds depends on y. It goes from y to 2. And then after that, I will do the integral in y from 1 to 2. Okay. Now again, you do the integration keeping y fixed. So y is like a constant. That's why you see it here. And do y is a constant. You see it here. And you're integrating x and you get this. Now you replace the bounds, 2 and y. And after you replace the bounds, you shouldn't see any x because they all integrated. Okay. So once you put the bounds, you get these things and there's no longer any x, so you're fine. Okay, and then it's simple one-dimensional integral in y. I skip the steps, you get this. You replace the bound as usual and you get 3, which is the same answer we got before. If you don't get the same answer, there's a problem. Either your function is really strange, which we won't see in that class. So if you don't get the same answer, it's because you made a mistake. All right? So we'll do more examples in class to get the mechanics going. But again, the most important thing, and if you understand that, you'll be fine for chapter 13, is those 3 steps. First, make a picture, decide of the order of integration and get the bounds, and then integrate. All right, thank you.